Okay, so we've got this disk in place there, the bigger one, disk B, and the smaller one, disk A, is going to come up, boink, pop right into it. All right, and they're going to collide. Now, what we have here in our picture, that's our before situation. And the smaller disk is coming up at a speed of 3. All right. What we really need to do is have an after picture as well. So let's begin with that for afterwards. Okay, after the impact, A's got a velocity of 1 parallel to the positive x-axis. So that means that A is heading here, something like this. Okay, now B then has to be moving somewhat to the left, all right, since A is moving to the right now. And since A is not moving up at all, B's got to be moving upwards somewhat, okay? So that means B is going to be something like this, okay? Now, we don't know that angle or anything yet, okay? So we got to figure out a speed and the angle, all that sort of thing if we need it, okay? But what I want to go ahead and do is get some more information out here, all right, so that I've got it handy. For example, I need to know that MA is 2 and MB is 11, okay? Again, it's good to write those things down. And now let's get our velocity components. VB is pretty easy initially. Let's go ahead and write it down though. So I've got VB x initial is 0. Yes, that's 3 subscripts. Okay, woo! I don't know if you've ever done that before, but you have now. So VBXI is 0, and similarly, VBYI is also 0. Now, for our other one, VAX initial is 0, and VAX, Y initial is 3. Okay, straight up just like that. So I've got my before components labeled, all right? So now I want to do the same thing with the afterwards, after impact components. So VAX final, that's 1, but VAY final is 0. But then I've got some VB final X, which we don't know what it is, and some VB final Y, which we also don't know what it is, okay? Now, they don't give us a coefficient of restitution, all right? But that's okay. That's all right. Let's think about what we've got. We've got 2 unknown pieces of information, right? The final velocity for X, the final velocity components for B at all. We don't know any of those things. But we know everything about what's happening with A before and after the collision. So since we know everything that's happening to one of these objects, then the coefficient of restitution doesn't come into play in our calculations, all right? We usually use the coefficient of restitution when we don't know the exact outcome of a scenario, like we did in that first video, okay? So what we're going to end up relying on here is our conservation of momentum in 2 different directions. So if we go with our X directions here, all right, initially my AX is 0 and my BX component is 0. So I've got 0 is my, so this thing's kind of like an explosion in terms of what's happening horizontally. Now that's initial. Now my final then, if I look at A, I'm going to have here MA, VA final X, and then we're going to say plus, although, you know what, let's go ahead and do this as as a magnitude. So that means I'm going to turn it into a minus. MB VB final X. Boom, just like that. Oh, that's pretty cool. Let's follow that a little bit further. We know VA final X, that's just a number. We know MA, we know MB. What we don't know is VBF X. Okay, we're trying to find about B. So, do a little bit of algebra on that thing. VB final X. Okay, it's just going to be VA final X. All right, and then the ratio. MA over MB. And, you know, in momentum problems, we see ratios like this all the time. And I want to encourage you to do your algebra this way so you can visualize those ratios so you can really get a better sense for what's happening in the scenario. Throw some numbers in here. VAX final is 1. So I got 1 meter per second. And MA we said was 2 kilograms. MB is 11 kilograms. Just like, why did they choose 11? Of all the numbers, there's an infinite number of numbers. You chose 11? Really? All right. So we work all that out and we get that VBFX is 0.1818. Okay, and again, I'm gonna tag that extra digit around just in case I need to use this in the future. Okay, now let's go in here and get what's happening with the Y components. Now, in terms of Y, there is no, I mean, for B, it's 0. There's no momentum there, but we do have momentum for A. So we'll do that. So MA VAY I. Okay, and then A afterwards, A has no vertical momentum. Only B has vertical momentum. All right, and so we'll put that in here. VB Y final. Okay, and that's what we're searching for. So we do a little bit of algebra. VBY final, and that's going to go as VA Y initial MA over MB. Okay, and plug in on that thing. That's a 3 meters per second. Again, our 2 kilograms over 11. And VBY final turns out to be 0.5454. Well, that is a fun thing about using 11 in the denominator. You get these fun fractions. 0.1818181818 0.54545455. Okay, so maybe somebody was feeling jovial when they were writing this problem. I don't know. Okay, there we go. So at that point, then you've got your components, so you can Pythagorize them to get the actual speed, if that's what you need in order to enter into the Mastering Physics solution there. Okay. All right. So, like I said in the first video, a lot of times in these two-dimensional situations, you're going to just end up using conservation of momentum 2 times. Okay. And if you don't see a coefficient of restitution given to you, that probably means you've got enough information in the problem without it. Okay. Again, like I said, usually when they give you a coefficient of restitution, that is going to mean you don't know the outcome or enough about the outcome to do that. Okay, so you could kind of imagine in this situation here, what if they hadn't told us where A was going? Right, it comes up and then boop, it goes somewhere we don't want to go. All right, then we would definitely have to have the coefficient of restitution. All right, there we go, guys. So let's get ready for the third video. Okay. And in the third video, we will be using the coefficient of restitution in it's I like to say it's an interesting problem. How about that?